Okay, let's get started. We're very happy to have David Kolchmeyer here to tell us about JT gravity with matter as a matrix integral and the ETH.
Right, yeah, thanks, Tom, and thanks to all the organizers for organizing this conference and for inviting me to speak here. It's my pleasure today to tell you about JT gravity with matter as a matrix integral and the ETH. And this work should appear soon, hopefully, with Daniel Jafferis, Bauer Mukametsanov, and Julian Sonner. So to introduce the subject, I'll just start by making some general comments. So let's consider a single non-disorder averaged holographic CFT with large N. So in this context, the eigenstate thermalization hypothesis basically says that the CFT data involving the heavy operators should look like some typical draw from an ensemble. So to be more precise, when N becomes large, the spectrum of black hole microstates becomes denser and denser, and so there should be some statistical description of them. And to be even more precise, we could imagine, for example, picking some microcanonical Hilbert space with some energy E, and we can consider matrix elements of light operators within the black hole microstates from this microcanonical Hilbert space. And there are many such matrix elements, and they should have some statistical description, like a mean, a variance, higher moments, and so on. And these, descriptions of the ensemble should vary as a smooth function with E. And in this talk, we can define what we mean by coarse graining to say that we forget about all the details of the black hole spectrum, and we just instead use an ensemble to compute simple observables. Right, so as mentioned, for the purposes of computing simple observables like thermal correlators of an order of 1 number of light operators at sufficiently early times, we really only need to use this ensemble that we got from coarse graining. We don't need to know the details of what the black hole spectrum was and all the coupling constants of the heavy operators and so on. So with that said, our only tool really for figuring out what this coarse grained ensemble is to use the gravitational path integral. So we think of this ETH ensemble as being constrained by the gravitational path integral calculations that we know how to do. So things get interesting because there are some gravitational path integral calculations that we do not know how to do. And namely, I have in mind particular calculations that involve wormholes. So to be more precise, in my mind, I'm considering JT gravity coupled to matter. We'll specialize to that case soon, but we could also argue more generally. Here's a two-sided wormhole in ADS, and B refers to just the size modulus of the wormhole, like the size of the neck. And when B becomes very small, then the local temperature of the bulk field becomes large. And hence, in the off-shell path integral, we expect there to be a UV divergence, meaning that this quantity, strictly speaking, isn't well defined. With that said, though, there are ways you could avoid this problem. For example, you could insert like a matter operator, like one matter operator on each boundary. And you could take the scaling dimension of the matter operator to be large. In the G Newton goes to 0 limit, and then that can compete with the gravitational action and allow you to localize onto a saddle at large B. So there are techniques by coupling the two boundaries to get a saddle, in which case you don't have to worry about this small b divergence. But this doesn't mean that every calculation will have a saddle, and in some cases you have to worry about this. And the reason why the wormholes are important is because they should contain more information, again, about what this ETH ensemble is. So what this means is that we need some principle that fixes this ETH ensemble other than the requirement that it reproduces gravitational path integral calculations. So for instance, such a principle could be choosing the maximum ignorance ensemble that's consistent with all of the calculations that we know how to do. And I'll come to hopefully a more concrete construction soon. Okay, so in order to be more precise and to give you a more precise setup, we're going to specialize to the case of JT gravity minimally coupled to a bulk scalar field. And the ensemble that we consider as like an ansatz for the ETH ensemble will be a random matrix ensemble. So the matrix models that we consider in this talk will be single trace matrix models with two matrices. So these take the following form. So O and H are Hermitian matrices, and the measure is just the standard flat measure on the real and imaginary components of these two matrices. Here, V of OH is just an arbitrary linear combination of words that you would make with the letters O and H. And we put all of this into a single trace. So basically, we're just considering the most general kind of single trace two matrix model you could consider. And we're restricting our ansatz to single trace because this will be enough to reproduce the correlators of interest in this model. And also because intuitively having a single trace means that, in the connection to 2D gravity, that the 2D gravity theory is local intuitively. And we want our gravitational path integral to reproduce a local theory. Furthermore, we want H to be interpreted as a Hamiltonian of some disorder average quantum mechanics. And we want O to be interpreted as an operator that's dual to the bulk scalar field that you just got from the extrapolate dictionary. I got cut off a bit. Right, so what I'm going to do later in the talk is motivate a specific choice of the matrix potential V. And so in order to figure out what this matrix potential is going to be, we're going to discuss a property of the algebra that's generated by O and H. Yeah, is there a way to make it like full screen? Or that work? I mean, okay. Okay, that's good. Thank you. Right. Anyway, so I'm going to make some comments about the algebra that's generated by the operators O and H, and that'll inform a choice of the matrix potential. So as some of you might have already figured out, these matrix models could be thought of as a generalization of the Sod-Schenker-Stanford model that was dual to pure JT gravity. So let me just, in one point, review their work. So there they found that pure JT gravity was dual to a Hermitian single trace one matrix model. So here we can compute the partition function, trace e to the minus beta h. This is just the expectation value in the ensemble. And by writing disk here means I'm working to leading order in the genus expansion or the large n limit or the large e to the S0 limit in the double scaled case. And what the matrix model does is it requires us to sum over all TÜV diagrams with topology of the disk. And then the point is that this disk computation in the matrix model also agrees with the disk computation in GT gravity, where we integrate the metric over all the configurations with disk topology. And this is the answer you would get in pure JT gravity. So when it comes to the generalization with matter, this is the picture that you should be having in your mind. So here I can use my operators O and H, or my matrices O and H, to compute a thermal two-point function, just like this. And then again, I just feed this into the ensemble average. And as before, we're going to be working to leading order in each of the S naught, or leading order N, leading order in the genus expansion. And so now that we have two matrices, when we write down our TÜV diagrams, we have to use two different colors. So here a red double line refers to the propagator of the O matrix, a black double line refers to the propagator of the H matrix. And again, we have to sum over all planar graphs. This is an example of one of the infinitely many planar graphs that we have to consider. And basically the claims that we can write down, or at least argue for the existence of, two matrix models where when you sum over all the TÜV diagrams like this, it equals what it's supposed to equal in GT gravity plus matter. So on the right-hand side, I drew a picture of what this is supposed to equal in GT gravity plus matter. And so let me explain it. Here, this black circle is a thermal circle that's at the boundary of the Euclidean disk, or the boundary of Euclidean ADS. And this blue line over here refers to the bulk two-point propagator of the scalar field. And to compute the holographic two-point function, we just take those 2 points and extrapolate them to the boundary, and that's what's being shown over here. So this is just a representation of the holographic thermal two-point calculation. But something that's nice is that this diagram here also can be converted into a very specific explicit formula using a set of diagrammatic Feynman rules. So basically by looking at how, the places where the blue line intersects the black line, or by looking at self-intersections of the blue line, which we'll consider later, we can, apply Feynman rules and get a specific answer. And that's the target for this matrix model. So you should always have this sum over TÜV diagrams in the back.
I have a naive question. So,
Yeah.
the rules you said from the matrix model side sounded like they treated H and O in the same way, but the bulk thing, I think, if I understand, does not. Yeah, I mean, the matter seems to be treated differently than. For
Right.
example, there's propagating matter, but there's not propagating gravity and so on. So yeah, how do I think about that?
Well, the matrix potential isn't going to be symmetric in the two matrices, so one will be preferred.
But you're somehow going to have to pick that
Yeah.
if you just sort of have an arbitrary potential.
Oh, sure. For an arbitrary potential, yeah. So we'll choose a potential in a way that kind of distinguishes the two roles of these two matrices.
Right. Thanks.
Right. Oh yeah, in the back.
Sorry, I'm afraid I can't see the colors very well, but do you have interaction vertices for the O operators in this picture?
Sorry, can you say that a little louder?
Do you have interaction vertices for the O operators?
Yes, you're kind of anticipating where I'm going. I'm going to start by not having interaction vertices and then introduce interaction vertices. Yeah. Okay. So this is just a brief review slide of JT gravity plus matter. So again, we're taking JT gravity and minimally coupling it to a scalar field. So the scalar field only talks to the metric directly, not the dilaton. Here S naught is the extremal entropy, chi is the Euler characteristic of the manifold we're considering. We're using standard boundary conditions where we fix the boundary length in dilaton. And furthermore, the scaling dimension of the boundary operator is delta and is related to the mass of the scalar field in this way. The plus or minus sign just corresponds to a choice of boundary condition. And in this work, we've only considered the case where delta is positive. Okay, great. So now that I've kind of introduced the arena that we're working in, our current task is now to construct a matrix model that reproduces all of the disk endpoint correlators. So at this point in the talk, I'm only talking about disk correlators, and the double trumpet is like part 2 of the talk. So let's just talk about the disk correlators, like what I showed you before. Okay, so here's a toy model. This is like our first stab at the problem. So here we're considering, again, a single trace potential, and I'm writing it in the energy eigenbasis of the Hamiltonian. So this is just, trace of V, and here, this is, I'm basically making an ansatz that allows for the most general terms that are quadratic in O. So here OAB refers to the matrix elements of O and the energy eigenstates. And F is a function that will fix to be something later on. Okay, so we'll start with this model. So now let's compute the 2-point function. So here's the 2-point function. In the next line, I kind of just did a trivial rewriting of this just to make some of the indices explicit here. And then in the line after that, I did the Gaussian O integral. So that gives me a 1 over F. And also I changed this sum over the indices A and B to be an integral over density of states. So here rho sub H is the density of states of the matrix H. And I just rewrote the sum as an integral of the density of states. But the point is that these density of states are also subject to the ensemble average. And so in the next line, this is where I make the disk approximation. So to leading order in the genus expansion, this will factorize into a product of 2 different density of states, which I'll call rho naught. And so this is just the computation of the 2-point function. So the neat thing is that the gravitation.
David, I apologize.
Sorry.
You used the word Gaussian and also single trace when you were describing this formula, but to me, like, it's neither, because you have the trace of O squared times something that depends on H. So that doesn't look like a single trace, and it also doesn't look Gaussian.
Okay,
Maybe
so
I'm just missing something.
that's
trivial.
fine. So I'll start with explaining why it's single trace. So I defined what I meant by single trace a few slides ago, right? Oh, okay. So let's take this function f and let's expand it in a power series. So each term in the power series is EA to the some power, EB to the some power.
Yeah.
And so now that particular term corresponds to a trace with H to that power times O times H to the other power times O.
Okay.
And that's a word made out of the letters O and H. And
Good,
so single trace. And then
Yeah.
next, why is it Gaussian? By that, I just mean that this action here is quadratic in O. And so we can evaluate the O integral using a Gaussian integral.
Okay.
Computing rho naught is difficult.
Yes, because H appears in the second term. as
Yes,
well.
computing rho naught is difficult because when you integrate out O, then the potential for H becomes multi-trace, and you'd have to find the saddle point for that. So yeah, that's hard to do, but the point is, all I have to do is argue that it's possible, and it is. So the point here is that the gravitational two-point function, just from the gravity calculation, actually takes the exact same form. It's literally the same formula here, except it provides us with specific formulas for f and rho naught. And so now I'm going to design this, this matrix model here to reproduce those functions f and rho naught. So now going forward in the talk, the functions f and rho naught are fixed to specific functions that I haven't written here because it's not terribly important. But for those who are more familiar with JT gravity, rho naught is the sinh square root of E, density of states. And this f is going to be 1 over a product of gamma functions. Okay, so basically we're just matching our ansatz to the gravitational two-point function. Now we ask about the 4-point, sorry. I need to draw a picture of this. This is important because I'm going to be using this kind of notation a lot. So the matrix model calculation is summarized on the left side of this equality over here. Each of these red lines corresponds to, so there are 2 red lines you see here, and those correspond to the A, B index over here. So of course, TÜV diagrams are much more complicated, and I'm only drawing what happens to the A, B indices. That's what these 2 red lines are. And we should think of each red line as corresponding to, well, an energy or an index, right? And then this double line over here corresponds to, a propagator. And the Feynman rule for this propagator is a function of 2 energies, namely 1 over f. Okay. And again, I just reproduced this picture here of the gravitational calculation. And basically, the thing that got this project off the ground is just that these 2 pictures look awfully similar to each other. But now we have to explore this idea further in the 4-point function. Okay, great. So here's the 4-point function, some thermal 4-point function. And so first we'll start with the matrix model calculation. Sorry, let's actually talk about the gravitational calculation first. That's on the right-hand side. So on the right-hand side, we have 4 insertions of the bulk field extrapolated to the boundary, and there are 3 Wick contractions you do, and I've drawn them here. Okay, now what does the matrix model say? So the matrix model, so again, we have 4 O insertions over here that correspond to, these 4 double lines that come out to the red boundary circle. And again, we have to do a Gaussian integral, and there would be 3 Wick contractions, except we're only working at the level of the disk. And so this means that we can only include planar diagrams. And so the only planar diagrams we can draw are the ones that are shown here. The third thing that you might want to draw, like a cross, is not planar, and so it doesn't contribute at this order. So clearly, the Gaussian model I wrote down got the wrong answer for the 4-point function. But it did manage to reproduce these 2 uncrossed Wick contractions. Okay, so let's talk about the last diagram here that we missed. So as I mentioned, diagrams like this can be evaluated using a set of Feynman rules, and so I'll kind of introduce them here. So you notice that we have 4 different regions, and each region will correspond to an energy parameter. So here I have an energy EI where I goes to 1 to 4. And the rule is that if the region is closed off like it is here, then we're going to be integrating that energy over all values using the disk density of states, rho naught. And furthermore, these black lines on the edge are are supposed to represent insertion of e to the minus beta h. And so I put an e to the minus beta e over here. The next Feynman rule is that whenever you have a blue line that meets a black line, you're supposed to put in this function. You're supposed to put in this f function over here, which I introduced earlier. It's a function of the two adjacent energies. That's not terribly important. This f function isn't terribly important in this talk. The real star of the show in this talk is going to be the function you have to include every time you see an intersection of two blue lines. So when you have an intersection of two blue lines, you're instructed to put down this new special function called a 6J symbol of SL2R. It depends on the 4 adjacent energies to this intersection. And this has very important properties that we will exploit later. So the first is called the orthogonality or unlacing identity. Basically, it just says that you can take 2 of these 6J symbols and integrate them like so, and you get a delta function. So depicting these kinds of identities is going to be a lot easier if I use a graphical notation. And so I'm going to introduce it now and use it throughout the talk. So here you see I have 5 different regions, and each one is labeled by an energy parameter. And so the Feynman rule just says wherever you have the intersection, you get the 6J symbol. So here we have E1, E2, E4. So that's this 6J symbol. And then the Feynman rule also says wherever you have a region that's closed off like this, then you're supposed to integrate over that energy with the disk density of states. And on the right-hand side, this equals a delta function. And so the graphical representation of a delta function is where I try to assign 2 energies to the same region. And basically the Feynman rule says, okay, those 2 energies should be the same. So good. So anyway, so we can represent, complicated looking equations by this simple identity here, and it looks really nice because you can think of 2 lines that you kind of unlace and separate them. Okay, so to get some practice, let's consider another identity here. This is the Yang-Baxter identity, and again, every region has an energy label. You write down the 3 6J symbols this time, and you do one integral, and this is a non-trivial identity that has this nice graphical picture. So I'll use this, this is good to know also. Okay. Okay, good. So now at this point, I've introduced 2 different answers for the 4-point function. First, there's the answer from the holographic calculation, which I'll call the correct 4-point function. And then there's the second 4-point function, which is what we got from the Gaussian model. I'll call that the incorrect 4-point function. And so in order to understand what's going on here, what I want to do is take our 2 4-point functions and go to the semi-classical limit, where now they become conformally invariant, SL2R invariant 4-point functions. And it's easier to think about what's going on if we take this limit. Eventually, I'll go back away from the limit. Okay, so first let's do 4-point conformal block decomposition of the correct 4-point function. And so what we learned from this is that the primary operators that appear in the OPE, aside from the identity, have dimensions 2 delta plus a non-negative even integer. This is what you also might be familiar with from generalized free fields in 1D CFT. Okay, now let's do the same thing, the 4-point conformal block decomposition with the incorrect 4-point function. And so what you'll find is that aside from the identity, the primary operators that appear in the OPE have dimensions 2 delta plus a non-negative integer, including both even and odd. And so I basically want to argue that this difference in the spectrum of the OPE is the reason why the Gaussian model got the wrong answer. And this is going to motivate kind of the fix I want to introduce. Okay, so here I've written down a condition that if we kind of impose it on the operator O is supposed to give us the correct spectrum. So let me explain what we have here. Here I'm taking 2 O operators, and I'm considering them at separated Lorentzian time. So here this T1, T2 is a Lorentzian time. And if you take their commutator, the condition I want to impose is that they equal this particular function of the difference of the 2 times the identity operator, and no other operators appear. This is something I want to kind of impose as a condition. And so why am I doing this? Well, basically, if we want to evaluate this commutator, we're just taking the difference of 2 different OPEs. And if any operator appeared, aside from the identity, in that OPE that had a dimension other than these correct dimensions that we want, then it would make a non-trivial contribution to the right-hand side of this commutator. And so by imposing this condition, we say that cannot happen. And so this should be equivalent to the condition that the only operators that appear in the OPE, aside from the identity, have these correct dimensions. So basically, the logic is that there's actually a bootstrap result, which says that if you have this condition on the spectrum and you also have associativity of the OPE and of course conformal invariance, then that fixes the 4-point function to be the GFF1. And so the logic is this is a constraint we want to impose in the matrix integral by hand, so that we impose this by hand. The next condition we need is associativity of the operators, but that's kind of built in to the formalism, or that's like guaranteed for us because we're representing these operators as matrices, and matrix multiplication is associative. And then the last condition is conformal invariance. I think that's also kind of built in by the nature of the special functions that we're using. Okay, so that's kind of where, that's how we're going to try to get the right ensemble. So, okay, good. But before we do that, I have to go back away from the semi-classical limit now. So we basically want to take this condition I imposed on these operators, and we want to back off from the semi-classical limit, and we want to write down an operator equation that's obeyed by the operators H and O, and then that will be imposed as a constraint in the matrix ensemble. So basically, our way for looking for this was to look for some operator equation that's quadratic in O. And so this is what we found. So I should explain this a little bit here. For simplicity, I defined this new matrix R where I just rescale the matrix elements of O in this particular way, depending on F. It's not terribly important, but morally, this is supposed to be equivalent to this condition, but away from the semi-classical limit. So the best way to explain where this is coming from is to draw some pictures. Okay, so here's our 4-point function again. Now let's consider the OPE of these two operators. So here, this contraction basically is the contribution to the 4-point function from the identity in the OPE. And so the thing that we're going to consider inserting into a correlator is going to be the two O operators, but minus something that amounts to some function of the Hamiltonian. And so when you insert into the correlator the two O operators minus the thing that appears, like minus the identity contribution to the OPE, then that has the effect of basically getting rid of this first diagram here. So now we're left with these two diagrams. Okay, so good. So we insert this thing in brackets into a correlator with two other operators, and then it's computed by these two diagrams. I also got rid of the black lines that kind of circle the whole thing because each black line corresponds to inserting e to the minus beta h into the trace. And I imagine that we went from like canonical to microcanonical ensemble. So each region here is a function of an energy using the kind of notation I introduced to you before. Okay, great. So now let's take this as a function of 4 energies, and I want to multiply it with a 6J symbol. And so using our graphical rules, I just have to draw an X on the bottom over here, and this should tell you, it's a 6J symbol of 4 energies, and you should be able to know what those energies are. There's this new energy on the bottom here, which I'm introducing, but that's okay. Basically, our constraint is like a 1-parameter family of constraints. Good, and so now I want to do a sum over an energy that I called B over here. So this is just the sum over the closed off region over here. And here, so originally I had a delta function, and so when I do the sum, it just cancels that delta function. So anyway, so I multiply by the 6J symbol here, I integrate over an energy, I get this picture, and now I use this unlacing rule I introduced on the 6J symbols. And so this unlaces, and so we get this, but this is what we started with. So it's the same thing as introducing this term in brackets and not doing the sum, which is why I put a Kronecker delta over here. So basically the upshot is, this is the matrix integral we want to consider. So I identified this operator equation. It's obeyed by the operators O and H in JT gravity plus matter. And now I want to square it and add it to the potential with a large coefficient, which I call lambda. And the point is that I'm going to take lambda goes to infinity, and so we'll impose it as a constraint. And then giving the arguments I gave before, we anticipate that this should reproduce the correct 4-point function and conjecturally higher point functions as well. Here, I also put an extra V of H in, which just has the role of making sure that the density of states of H is the sinh. Okay, so this is a nice construction, but the question is, can we actually test this? Like, is this idea testable? And so this is what we have to test it. So first, I'm going to take this expression here, which depends quadratically on the matrix O, and it depends on the 6J symbol. So when I square it, I'm going to get a potential that is quartic in O. So this will provide the interaction I was referring to earlier. And it actually turns out that this potential I wrote down is a single trace matrix integral, and it's quartic in O. And so now I'm just going to do kind of the naive thing, which is to read off diagrammatic rules. So in particular, I can read off a tree level propagator from the inverse of the coefficient of the two O's. And then I can also read off a tree level 4-point function from the quartic term. And so as before, each red line here is supposed to refer to an energy, and then this Feynman rule is a smooth function of the external energies. And then the explicit formula is given on the right-hand side, where I'm using my notation I introduced earlier to introduce 6J symbols and delta functions. One thing I should say is that the integral that's represented by this loop over here is actually divergent, but this will cancel out, as I will in what I'm about to show you. Okay, so we have some Feynman rules. So next I want to introduce a Schwinger-Dyson equation of this matrix model. So here, this red blob refers to the sum over all planar 2-point functions. So of course, in the Gaussian model, it would just be like the tree level propagator, but this is an interacting model. So we have to consider all loop corrections and everything like that, but still planar diagrams. And so basically all this equation is saying is that let's pick this left double line propagator over here. And so there are two things it can do. First, it can either connect directly to the other side, which is what I've shown here, or it can end in a vertex. So here's the vertex that it ended in. Now you have 3 more double lines coming out of the vertex, and they have to get together with the last double line in all possible ways. And so this red blob over here refers to the sum over all planar 4-point functions. And so this is a Schwinger-Dyson equation, and basically what I'm going to do is, we know what the 4-point function and we know what the 4-point vertex and tree level propagator are, and we know what we want the red blob to be. The red blob is going to be the 4-point function that we want to reproduce. It's supposed to be the gravitational 4-point function, because this is the sum over all the planar 4-point diagrams. So we're going to basically just check that this Schwinger-Dyson equation is obeyed. Well, so the matrix potential is the square of this thing I called M, and M is quadratic in the matrix. So now the matrix potential is quartic. So there's a quartic vertex only in what I've shown you. Right. Okay, so we have some Schwinger-Dyson equation, and we want to check it. So, this large lambda limit has to be important, of course. And so it appears in the following way. So this tree propagator over here is 1 over lambda, and so it'll drop out in the large lambda limit. On the other hand, here we have a tree propagator, which is 1 over lambda, but the 4-point vertex is lambda. So in the large lambda limit, this is just order 1. So basically, I'm just going to forget about this first term over here. And so we just have to check the second term equals the thing on the left. Okay, so as I mentioned before, the sum over all planar 4-point diagrams, well, we want to check that it equals this, the correct gravitational answer. So I'm going to substitute this into the Schwinger-Dyson equation and also substitute in our gravitational rules. And so let's compute the second term on the right-hand side. So here you recognize this as coming from the 4-point vertex. And on the right-hand side, we recognize the 3 Wick contractions for the final answer. And so we'll multiply these things together and collect all the like terms, and this is what you get over here. So now the key point is that this term over here is actually 0, thanks to my unlacing rule. So this circle can be moved through the line, and so these 3 terms cancel out. And so we're left with just the first line over here, but this is exactly canceled by the tree level propagator, so that on the right-hand side, we just get 1, and that's what the left-hand side was equal to. So basically, we just checked at least formally, that the model I wrote down obeys these non-trivial Schwinger-Dyson equations. And so it's a nice verification that this works, and we can do similar checks with other Schwinger-Dyson equations. Okay, so anyway, this was a nice idea, but what lessons are we learning here? So let's go back to thinking about general holographic theories. So let's suppose that somebody told us the operator algebra that governs the light operators only. So maybe you got this by doing some bulk effective field theory calculation. The idea is that the part of the algebra involving the light operators is something that you should be able to compute. So now we can consider an ensemble by averaging over all of the CFT data involving the heavy operators, but subject to the constraint that the algebra governing the light operators is preserved. And so that's basically what we've done here. So again, we impose a condition on the spectrum of the OO-OPE, which given associativity and conformal invariance will uniquely fix the OPE coefficients and hence the 4-point function. And by thinking about these Schwinger-Dyson equations conjecturally, this also gets the higher point functions right too. This result, this bootstrap result I mentioned, is attributable to Mazak and Polos. One thing I should say is that crossing symmetry among heavy operators doesn't have an analog in our JT example, but if you wish, you could also try to, impose crossing symmetry as a constraint by squaring it and adding it to the potential of your ensemble. But I haven't really thought about that too much. And finally, there's some sense in which this ensemble that I've constructed is maximally ignorant. The reason why is because the operator equation I identified involving O and H is obeyed by any theory whose correlators are given by the JT plus matter disk correlators. This includes the SYK model, and this includes any other model that might have the same symmetry breaking principle as the SYK model that might have led to these correlators. So in some sense, where our ensemble average includes the SYK model and many other models too. So in some sense, we might call this a maximally ignorant ensemble, and it seems to have a semi-classical gravitational dual. Well, I guess in order to say that definitively, I'd have to talk about other topologies. But that's what I'm going to get to in the second part of my talk. Are there any questions at this point before I, yes?
If you consider a microcanonical window in energies,
Yes.
then you're saying that the matter theory is just a quartic matrix model.
Yeah, so this is a good question. So, I mean, we consider different approaches for constructing matrix models, and here I've only given you one approach. So in my mind, there are two different ways we thought about how to get the matrix model. One of them I call working forwards, one of them I call working backwards. Here, I told you about our working forwards approach, where you write down a potential and argue why it should give the correct answer and do some checks. But there's also the work backwards approach, which I wasn't going to talk about due to lack of time, which is just that if someone gives you all the gravitational correlators, including endpoint correlators and higher, there's an algorithmic way you could kind of work backwards to determine what the matrix potential has to be to reproduce that. But actually computing the matrix or determining the matrix potential in this way is tedious. So maybe your question is, how do these two approaches relate to each other? And the answer is, I don't exactly know.
I think I messed up something more pedestrian. I'm just saying that I would have naively thought that for a microcanonical window, the matrix model that describes all moments of the operator O would be some very complicated thing. But I think you're saying that it's just at most quartic.
Yeah, that's right. Yeah, so the matrix model isn't necessarily as complicated as you might have thought. It seems that a quartic matrix model will reproduce at least the disk level correlators.
So you could reproduce all moments of O, for example, just with the model.
Sorry?
You solve the quartic matrix model, and you can reproduce all correlators from just this one parameter.
Well, yeah, I mean, that's the conjecture. I call it a conjecture because our verification of it with Schwinger-Dyson equations may have felt a little formal, given that we were working directly in the double scaling limit. But this is the idea we want to present. Yes, that you can, identify all the relevant constraints like crossing symmetry and then square it and add it to a potential with a large coefficient. And so, yeah, and so then it seems like having a quartic kind of interaction might be or appears to be the minimal kind of thing you would need. Okay. Maybe since I'm about to start a new part of the talk, maybe I'll ask how much time I have to figure out like.
You have maybe 15 minutes and then 5 for questions.
15 minutes? I think that's enough time to talk about the cylinder here. Okay, good. So, sure.
In the space of matrix models, this looks very special, right?
Yes, it does. I'm not necessarily going, yeah.
Well, in the space of gravity, this theory looks very natural in some sense. I mean, we could have asked this about the SSS also.
Mm-hmm.
Do you understand why, well, from the matrix model side, why we should pick this matrix model as opposed to some other one?
Right.
The question doesn't make sense. I mean, maybe you should say, well, gravity theories are special. That's it.
Right. Well, yeah. So, I mean, I'm not claiming this is the unique thing you could have done. But somehow the logic is, I mean, yeah, so the main lesson is, or at least the philosophical lesson is, you know, to identify all the operator equations that you would want to be true involving the light operators. And then, you know, the light operators make some algebra, and then we're just averaging over representations of that. And it seems that to impose the condition that the light operator algebra is what you wanted it to be, you know, the algebra, the relations that define the algebra are quadratic. And so if you square that, that's quartic, and then add that to the potential with a large coefficient, that seems to be enough to impose kind of the condition that you wanted, that the algebra of the light operators is obeyed, and then the heavy data just gets averaged over in all possible ways that obey those constraints. Yeah, so it seems like, yeah, so like philosophically, there is some simple principle that seems to do the job. It could also be more complicated. I'm definitely not saying this is unique. And also another thing is that if you're interested in going beyond the disk, then something that we were forced to confront in this work is the idea that the details of how you take the double scaling limit matter. Right.
Yeah, I thought there was, I mean, this has always confused me about this. I never understood it properly, but you know, there's such a thing as random matrix universality. So I thought at least some of the story isn't supposed to depend on exactly the details of the potential. On the other hand, clearly some of it does. So I
Right.
actually get a sense of how big, I don't know how big of a class of matrix models actually work.
That's right. Yeah, I'm not sure either how large the class is, but we found some examples, we think.
Usually random matrix universalities for things like the eigenvalue spectrum and very relatively near eigenvalues.
Right.
Longer. I mean, this isn't like more broad, the broad features of the
but
the eigenvalue distribution.
I mean, I guess he didn't tell us much about the Hamiltonian part of the matrix model, but I thought like for a fixed row knot, there should be lots of different matrix models that give the same row knot, right?
Yes.
Because maybe the lesson here is somehow the matter part is kind of less universal or something.
You consider like the very late time matter correlative.
Yeah.
Just throws that.
Yes.
Yeah, that's universal, but you discuss it then define.
Yeah.
Okay. So let's talk about the cylinder. So we're interested in the two boundary connected correlator in the matrix ensemble here. So again, I just take two partition functions, multiply them together, subtract off the disconnected part, and then leading order in the genus expansion, you're instructed to sum over TÜV diagrams with a cylinder topology. So I've just drawn an example of such a thing here. So in this and many other diagrams, the top part of the diagram and the bottom part of the diagram are identified. So now you see that it has the topology, this TÜV diagram has the topology of a cylinder. So for example, this single black line over here refers to, you know, the left trace. This single black line over here, which again loops around because we identify the top and bottom of the diagram, is this other trace over here. And you know, the sum over TÜV diagrams looks quite complicated. But one of the technical results of this work is that if someone gave you a matrix model, a two matrix model of the kind we're considering, and said, you know, here's the answer for all the disk correlators, then just at the level of the answer, you can go from that to figuring out what this you know, cylinder or double trumpet correlator is going to be, at least in principle, and in our case with JT gravity in practice. You have to know all the disk correlators, but the point is that the disk correlators are summarized by some nice Feynman rules. And so again, the technique is that if someone told you the disk answer, then they're basically telling you what the sum over all the planar TÜV diagrams is. And so the strategy is to take this sum, take these diagrams, some of which you know, and then to cut them up in some clever way and then reassemble the pieces. So now you have diagrams that have the cylinder topology. And so I'll walk you through that a little bit. Oh yeah, I should also say we also considered inserting an operator on each boundary. And that's actually what I'll talk about right now. So yeah, so let's say someone gave you the disk 2-point function. Here I put the red blob because we're considering an interacting model. So this means that this red blob, with these two red lines, is a function of two energies that you know. And so all we have to do is take these two single lines and connect them to each other in the other way to get something that has the topology of the double trumpet or the cylinder. And then we can actually evaluate the answer. And what do we get? We get the double trumpet with an operator inserted on each boundary. And this diagram could be evaluated using the Feynman rules that I mentioned before. But what it means is intuitively clear. We just inserted an operator on each boundary, integrate over the double trumpet. Okay, so we can go on. Let's suppose someone gave you the disk 4-point function. So here I've modified what I did because we have an interacting theory now. This blob with the C refers to the sum over all connected 4-point functions. It's the thing that the Gaussian model missed. And so now if someone is telling you this is true, then you know what this C blob refers to as a function of 4 energies. It's the 6J symbol. And so now I'm going to take this C blob and I'm going to amputate off the 2-point functions. Just going to calculate, consider the amputated 4-point function. That's the A blob. And then I can take this A blob over here and I can make a double trumpet, topology diagram out of it in the way that's shown. Again, the top and bottom of the diagrams are identified. And something that was important is that the red blob on this double line over here is missing. So before I identify the top and bottom, I have to remove one of the red blobs from the connected blob over here. Otherwise, I would be double counting cylinder diagrams. And so that's what I've done over here. That's what this notation means with this red blob in the bracket raised to the -1 power. And so now, again, we can evaluate this and the answer looks like this. So it's the same thing I had on the previous slide, but now I draw an extra geodesic, an extra blue line around the geodesic. And so what this means is that, so again, this diagram you could evaluate using the gravitational Feynman rules as before. And what it corresponds to is the 2-point function, but now the closed geodesic of length B is weighted by this amount over here. And we think of this as being something that would contribute to the partition function of the scalar field on the double trumpet. Okay. So I'm going to try to go through this really quickly due to lack of time. Basically, this is the next step in the procedure. So we have a connected 8-point function. We subtract off things that were already counted on the previous slide. And again, we have to strip off some diagrams before we make the identification.
Sorry, before you do the next diagram, just on the previous one.
Yeah, sure.
So that goes to infinity when B goes to 0. And so I should interpret that as being related to this divergence you talked about at the beginning.
That's right. So in this way, we can match the double trumpet answer, including the divergence, by breaking it up, by organizing it as a sum over things that look like this. Now, this is divergent too.
Yeah,
but you could expand this out. You could expand this geometric series out, and then each term in the geometric series is convergent.
Yeah, but so what people used to say about that divergence is they would say that it means that JT plus matter is not UV complete. It's some kind of non-renormalizability.
Yeah.
So whereas here, like you're somehow saying that you have a UV completion and it just has this divergence.
That's right.
It's not.
So, yeah, so
You worry about that, or that's fine?
I'll
or-
tell you exactly how to think about that from the matrix model perspective.
Okay.
That's like the last slide. How much time do I have, by the way? I don't want to like.
5 minutes plus 5 for questions, so you can eat that time if you want.
Okay, great. So, yeah, so I'll get there. Anyway, this is just supposed to be a more souped up version of the previous slide, but the reason why I introduced it is because there's an additional subtlety. So the diagrams I want to strip off from this class of diagrams before making the identification to avoid double counting, well, it looks like this. And the new subtlety is that there's an energy that appears in between these two legs, whereas on the previous slide, the only energies that appear in the problem are the ones associated to the left and the right boundaries. So in practice, if I want to strip off these diagrams, I have to basically invert an operator in the following sense. So here I already explained what this means, as the mathematical expression, but think of this as a matrix with two indices, E1 and E2. And so what we need to do is invert that matrix. We get a function of two energies and then integrate one of those energies against an energy that appears in the definition of this connected blob. And then that has the effect of stripping off these diagrams we didn't want before we make the identification. But the subtlety is that this matrix here is not invertible. If you multiply this matrix by itself, you would get something proportional to itself. So this is something that, this is where the technical details really blow up, and I don't want to go into that. But the point is, what I think this is telling us is that the details of how you take the double scaling limit to get the disk answer need to be known in order to execute our procedure to figure out the double trumpet. And so we had to consider ways of deforming the gravitational answer away from what I presented in such a way that this expression here is invertible. And we considered different ways of doing that. We gave names to our two different ways of deforming the answer. One of them is called Selberg regulator. One of them is called Q-deformed regulator. I don't want to go into the details, but the point is that they give you different answers for the double trumpet. This is just, I guess, another slide where I just write down the formula for the double trumpet. And here's the scalar partition function that you would include when you add matter. So the point is that the Selberg model reproduces this, but to be more precise, each kind of sum of diagrams is reproducing one term in this series. And we checked it explicitly for n equals 0, 1, 2, and 3. And then we believe the answer kind of extrapolates out. Anyway, so this is the partition function of the matter that we reproduce using our so-called Selberg regulator appears to be, at least to the extent that we checked, that of the scalar field. On the other hand, using this so-called Q-deformed regulator, we get a different partition function that looks like this. It also has bad UV behavior, but in a different way, because it has a Hagedorn temperature. When B gets too small, the denominator goes to 0. So you might think that maybe this model is garbage, but the reason why I like this Q-deformed model is because we have a principle for deforming it even further away from the double scaling limit, which is that it should agree with correlators in the double scaled SYK model that were computed by Berkuz et al., where the formulas for H and O in terms of SYK quantities is given here. So it might be an interesting model to study. Okay, so this is the last slide, and then I jump to the conclusions. Right, so as I mentioned, in both models, you have this problematic small b behavior, and now hopefully this will answer Daniel's question, what does this mean in the matrix model side? So for simplicity, let's suppose we integrated out O. So we just have some multi-trace potential for H. And also doing this calculation is a little easier if we take the conventional Tufts scaling, where the single trace term comes with a factor of n, the double trace term has no factors of n, triple trace term is 1 over n, and so on. So you might already know that the disk density of states is determined by the saddle point of this eigenvalue integral. On the other hand, the cylinder answer is determined by the Hessian evaluated at the saddle point. It's like directly determined. And so basically, this means that when the double trumpet is not defined, when you can have this problematic UV behavior in the matrix model side, so even though we were able to reproduce it, we were able to reproduce it with the matrix model where the saddle point is perturbatively unstable. So in SSS, their saddle point was perturbatively stable, but still maybe not non-perturbatively well-defined. Here, it's even worse. The saddle point is perturbatively unstable. And that's what having this divergence means. In other words, that explains why the sum over all the TIFF diagrams diverged, whereas in the usual one matrix model case, we're not used to that. Okay, so now I'll just conclude.
Sorry, but are you going to tell us what that means about gravity or?
I wish I could. I guess what I want to just say is I think we might have a setup for understanding how to think about this divergence. I mean, basically, what we want to do is do a steepest descent starting from this saddle and go until we find a new saddle and then recompute the disk answers and then see if that can be interpreted in some way. I don't know.
Who knows what's going to happen, right?
I have no idea. But
Yeah.
in principle, it's a question you can ask in this setup.
I mean, the disk seems
I guess-
fine, but, sorry, go ahead.
Yeah, so if you think of the two-dimensional theory as a string theory, right? So this is the tachyon divergence,
Right.
and you would need to condense this tachyon, which would be the same as looking for an arrow solution.
Yeah.
Somehow some instability in the space of in the third quantized version of the theory. Right?
Mm-hmm.
Yeah, but I
Mhm.
mean, that it's really telling you that something's serious, right? Like that the true ground state is some totally different thing that has nothing to do with.
Maybe it's close. You don't know.
I mean, we don't know. Yeah.
Right. Okay, yeah, so I'll just conclude here. Right, so the ETH ensemble is constrained by the gravitational path integral, but it can also teach us about wormholes once we provide some additional rules for how this ensemble should be constructed, such as the requirement that it's a maximum ignorance ensemble. So as mentioned, we want to find where this unstable saddle goes and give it a gravitational interpretation. I should also add that our way of relating the double trumpet to the disk is something that would apply in principle to any single trace two matrix model. And so we know in one matrix models, you can relate correlators using recursion. And so maybe there's some more interesting structure that remains to be discovered here. And we're just seeing a glimpse of it. I'm not sure. And again, I just want to say, I didn't give you explicit formulas for how I back away from the double scaling limit. But for this particular Q-deformed model that has close connections with double scaled SYK, we have explicit formulas. And so these could be interesting if we want to ask, what is the bulk dual of this model? Or what is the bulk dual of the double scaled SYK model? So I'll leave it with there. Thank you. I'll leave it there. Thank you very much.
Further questions for David? Okay, if there are none, then let's thank David again.
Thanks.